Hi, welcome back. In this lecture, I want to talk about the Bloch sphere and rotation in the Bloch sphere. We will see how quantum gates can be expressed as rotation in this graphical representation of a basic quantum state, which is the qubit. So the general state of a qubit is described with two complex numbers. You probably remember that we use two amplitude A and B that are multiplied by the ket 0, and B is multiplied by the ket 1. So these are our computational basis. And these represent our general state for the quantum system. So you see that here we have two amplitudes, A and B, and these are complex numbers, and therefore they have real and imaginary part. So we expect to have a four-dimensional real space when describing a qubit system. Surprisingly, I will see in this lecture that all the possible state of a qubit can actually be drawn on a surface of a sphere of radius 1, which is a two-dimensional object, right? It's a sphere, and therefore we will need just two parameters to describe it. So we can describe it, the quantum state, just using, for instance, two angles, one called theta, another one called phi. So let's look at quickly at the derivation. So first, the first step in our derivation is to take our quantum state that is represented by A and B, two complex number, and we move from the Cartesian description of complex number to the polar coordinates of the complex number. So any complex number as it can be written in a polar coordinate as formulated in this slide. You see we have R, that is so-called magnitude, and then we have an angle alpha. So if you go to the graphical description, you see that if this is our complex planes where we have the real part and the imaginary part, and this will be our complex number Z. We can use either the real part and the imaginary part, but also we can have an equivalent description that using R, that is the magnitude. This is the length of this line. And then we have an angle A. So whenever we move to polar coordinates, we switch the reference system by using an angle and a magnitude of the vector. So we use this trick. So we start from the Cartesian description of a complex number. So we have our A and B, and the first step is to use the polar coordinate. So we introduce R1, that is the magnitude, and then R1, R2, and then we also introduce alpha 1 and alpha 2. At this point, we still have four parameters describing our general quantum state. So let's start simplify a little bit. So we have a constraint whenever we have a quantum state is the fact that this, the modulo square of A and B must be equal to 1. And the reason for that is that these two guys are actually probability. So the sum of the probability, either to measure the quantum state in state 0 or 1, must be 1, because this is a probability. So we see that these constraints, so-called normalization constraints, will allow us to less one parameter. Because R1 and R2 must be equal or less than 1 and greater or less than 0, we can always find an angle theta such that we can express our magnitude of the complex number using an angle theta. We'll see later on why instead of theta we take theta over 2. Doesn't change much, but we're taking an angle to express both R1 and R2. And R1 is the cosine and R2 is going to be the sine. Note that once we introduce this formulation that is relying on the fact that the quantum state need to be normalized, then we can obtain this expression here. So at this point we have 3 parameters. So we saw how we could go from 4 parameters. We got the description, rely on the normalization constraints, and using 3 parameters now. So we still have these 2 angles, alpha 1 and alpha 2, and then introduce this theta angle to represent the amplitude of the quantum state. Let me say a few words about an interesting fact about quantum state. So whenever we have a quantum state psi and we multiply by a complex number c with an absolute values of 1, this happen without changing the state of the psi. And you can see from the linearity of any quantum transformation. So for instance, we have a unitary, and we apply this unitary of c, whose module is 1 multiplied by psi. This guy here can go out. There is no operation, either unitary transformation or measurement, that allow us to distinguish psi from c multiplied by psi, where c is a constant with modulo 1. So we call this c a global phase, and we have just shown that it is physically irrelevant because we cannot really distinguish physically between psi and c multiplied by c. So let's go back to our transformation. So we can therefore multiply psi by this exponential of minus I alpha 1 to obtain an equivalent representation and get rid of one phase. So in this case, we have theta and phi, where phi is equal to alpha 2 minus alpha 1. And we reach our major goal to go from 4 to 3 and now 2 parameters. And the 2 parameters are theta and actually phi. So welcome to the Bloch sphere. That's the graphical representation of the qubit. So using this representation here of our quantum state, we can map any quantum state to a point on this sphere. So let's look at how this sphere looks like. So we have 3 axes, x, y, and z. And then you see that we have our computational basis, that is 1, that is a classical bit. And then as the opposite side, here on the south pole, we have 0. We also have the plus state and the minus state on the opposite side of in the x direction. So we can describe the state of any qubit using 2 numbers. One is theta, and that is so-called polar angle, and the other one is phi, the so-called azimuthal angle. So any quantum state can be represented by a 3-dimensional point that takes this formulation, that locates our state qubit on the surface that, as I said, is called the Bloch sphere. Let's go back. Why in the transformation I say theta 2 and not theta? Well, if theta runs from 0 to pi to cover the whole range from the top to the bottom of the sphere. So this is why we use theta over 2 to represent our preceding qubit. So we only needed to get up to pi over 2 for our angles for the sine and the cosine. I want to make a connection now between the Bloch sphere and x, y, and the z gates. So these single qubit quantum gates that we saw in the previous lecture. So if a 0 here is actual map to North Pole and 1 is in the South Pole, then these states are orthogonal on the sphere. And we also say the same thing for the plus cat and the minus cat. These are the equator, but on the opposite side. So the x gate takes the 0 and transform to the 1 state and the state 1 to state 0. But also it leaves the plus and the minus state. So the X gate can be seen as a rotation along the X gate by pi. So the X gate acts like a rotation of pi radians around the x-axis in the Bloch sphere. The very same applies to the Y and the Z gates. So the Y gate is nothing else than a rotation of pi radians around the y-axis, and the Z gate is nothing else than a rotation around the Z axis of pi radians. We can express any general transformation, any general rotation along the x, y, and z gates. Instead of just pi, we can take an angle, theta, and this will be argument of our rotation. And here you can see what is the matrix formulation of this gate. So be careful with these three gates. We are going to use them quite a lot in the formulation of our parameterized quantum circuit. So this is some of the gates that we're going to use quite a lot during the course. At this point, it is also nice to talk about gate equivalence for Rx, Ry, and Rz. It can be proved that for any qubit gate, it exists a unit vector Rx, Ry, and Z, lowercase, and an angle theta such that we can express our gate using the X, Y, and Z gates. For instance, we can obtain another gate by doing this operation here on the slide. So this is quite nice. For instance, if on a quantum computing system we don't have the Hadamard gate, we can use the X and Z operator and gates to calculate the Hadamard gate. For one qubit gate U, we can also show that there exist three angles alpha, beta, and gamma, such that we can express any gate as a factorization of three gates, RZ, RY, and RZ, RY, and Z. Finally, in some quantum computing architecture define a generalization of a single qubit operation. This is called universal one qubit gate. And this universal quantum computing gate depends on three angles, theta, phi, and lambda, and this is the specific formulation using the matrix expression. So we can use this formulation to express any one qubit gate. This is the last slide of this lecture, and talk to you soon.